Today we are going to discuss the topic of consensus algorithm, Paxos and its variants. So what is consensus problem? Consensus simply means an agreement. Agreeing on a single value among group of participants when they might have different opinion. Okay. So we frequently use consensus in the distributed system design where we have collection of computer which need to agree on a single state to have the consistency. There are various reasons why we need consensus. To agree on who get access to a resource, agree on who is in charge, or to agree on a common ordering of event among a collection of computers. So what is Paxos algorithm? What is Paxos? First we will discuss what is Paxos. Okay. So Paxos is a family of protocol for solving consensus in a network of unreliable or fallible processors. Means our processor might fail or they are not reliable. And the Paxos algorithm is based on the majority rule. The majority rule ensures that only consistent resulting value can be achieved. Here majority rules means a value will be agreed only when majority of the acceptors say yes for that value. Okay. And one more thing in the Paxos, we simply, the goal of Paxos algorithm is simply to agree on a value. Which value will be agreed, we don't care. We just need some value will be agreed, and that value need to be consistent, of course. And the Paxos protocol proposes that if the majority of the node in the system are available, then the entire system is considered to be available and it can guarantee data consistency and the data availability. Okay, now we are going to look at a simple analogy how to reach consensus with Paxos. Okay, so there are a group of 4 friends. They want to do something in the afternoon, but they don't know exactly what they are going to do in the afternoon. So the first person initiate a proposal. Let's go to the cinema. The second person will agree with the first person proposal and it say, okay, let's go to the cinema. Now the third person, listening to their conversation, it proposes its own proposal. No, let's go to the dinner. The fourth person listening the third person, it say, okay, I am also in, let's go have to the dinner. Now to reach the consensus, some of the people need to change their mind, otherwise we can't reach on the consensus. Okay, so suppose the person first and person second, they change their mind. Okay, let's go for the dinner. So this is how a consensus will be reached in a group of friends in our analogy. Okay, so we are going to discuss some of the assumptions regarding the processor and the network which we will assume throughout our Paxos algorithm. Okay, some of the assumptions regarding the processor are: processor operate at arbitrary speeds, means processor might operate at different speeds. Processor may experience failure, means during the protocol a processor may fail. Processor may rejoin the protocol after failure, means during the protocol a processor might fail and it can rejoin the protocol from the same point. Some of the assumptions regarding the network are: processor can send message to any other processor. Messages are sent asynchronously and may take arbitrarily long to deliver, means there are various reasons in the network to deliver a message with latency. Message might get delayed to deliver. Okay, message may lost, may reordered or duplicated, but the message are delivered without corruption, means we are not considering the Byzantine failure. Okay, now we are going to look at a problem in basic Paxos. Okay, why basic Paxos are not sufficient. So when multiple proposers believe themselves to be a leader, we are going to take this example. Okay, so here client send a request to the proposer. On the behalf of client, this proposer means this leader send a prepare message with the proposal ID 1 to all the acceptors. Now a acceptor it don't have any problem with this proposal, so it send a promise message to the proposer and it place null value. Here it place null value because nothing is accepted by the acceptor till now. Okay, so now assume this leader get fail. Okay, there are various reasons of failing a proposer during the protocol. Now a new leader will be elected and it will send a prepare message with the proposal ID 2. This new leader know that last leader initiated a proposal with the proposal ID 1, so it will start a proposal by sending a prepare message 2. Now nothing is happened till now, nothing is happened, this acceptor didn't promise to reject a proposal with the proposal ID 2, so acceptor will send a promise message to all the acceptor here will send a promise message to the proposer. Okay, now let's assume that a old leader recover at this point. Okay, and we already discussed that a processor may rejoin the protocol after failure. So this leader send a prepare message with the proposal ID 2. Here it taking proposal ID 2 because previously this proposer this same leader initiated the proposal with the proposal ID 1. So here it will take a proposal, it will send a prepare message with the proposal ID 2. It will increment the proposal ID to send a new proposal. But as the acceptor already promised for the value 2, it will not accept this. It will reject this prepare message and send a negative acknowledgement that acceptor already promised for the proposal ID 2. So here the new leader will send a prepare message with the proposal ID 3 now. Okay, now the acceptor will receive this prepare message. Okay, and the acceptor didn't promise to reject any proposal with the proposal ID 3, so it will send a promise message to the proposer. Here null value are placed because nothing is happened till now. Here also accept message will be not initiated till now, so nothing is accepted by the acceptors, any acceptor. So all the acceptor are placing null value in place of value. So now here the new leader will send a accept message, as the new leader already received here promise message from the majority of the processor. So now it going to send a accept message, and its accept message is delayed basically, and there are various reasons that to delay message. Okay, so now this new leader is sending a accept message to all the acceptor, but the acceptor already promised for the proposal ID 3, it will going to reject this accept message. They are not going to accept this value, and sending a negative acknowledgement to the proposer saying that I already promised for the proposal ID 3, I can't accept it. Okay, so now the new leader will send a prepare message with the proposal ID 4 now. Okay, as now the acceptor will receive this prepare message. As the acceptor didn't promise to reject any proposal with the proposal ID 4, it will send a promise message to the proposer. So this process keep on going. Okay, when the multiple leader are trying to, here the multiple proposer are trying to overtake each other, and it might possible that it will never converge. So we can see here that basic Paxos are not sufficient. We can't just survive with the basic Paxos here. So now we are going to discuss multi Paxos. Okay, so we seen in our last slide that basic Paxos are not sufficient. So the basic Paxos require at least two network tip to reach a resolution. Two network tip, one network tip for the prepare and promise message, and the second network tip for the accept and accepted message. Okay. So in the case of concurrency means when multiple proposers are trying to propose a value at the same time, the algorithm is not sufficient, and in extreme cases it might even lead to the problem of a live log, which is inefficient. Okay, so to solve the problem of live log, multi-Paxos are introduced. Okay, in multi-Paxos, what we will do, in multi-Paxos we will elect a leader, and all the proposals are initiated by that leader only. So the live log problem is eliminated. Okay, and in the multi-Paxos, if the leader is stable means the same leader is trying to execute the next instance also. In that case, we can skip phase 1, means the prepare and promise sub phase. Okay, to achieve this, what we will need to do, we will have to include the instance number. When the acceptor is sending promise message, we will include an instance number in the promise along with the value. Okay, this reduces the significant amount of overhead, because we are not sending prepare and promise message unnecessarily. So lot of overhead of sending message is reduced. Okay, the multi-Paxos is nothing but executing the many instances of the basic Paxos protocol only. Okay, so in multi-Paxos, what we are simply reducing the two-phase process into a single-phase process. Okay, now we are going to take some example of the multi-Paxos algorithm. Okay, so in this diagram we are executing only one single instance of basic Paxos. Okay, so here client will send a request to the proposer on the behalf of proposer. Now on the behalf of client, this leader will initiate a proposal. It will send a prepare message with the proposal ID and to all the acceptors. Okay, now after acceptor receive this prepare message, as the acceptor didn't promise to reject any proposal with the proposal ID N, it will send a promise message to the proposer. In the promise message, it will also include the current instance number and the previously accepted value. Here VA, VB, VC are the previously accepted value by the acceptors. Here we are taking 3 acceptors, so they are the 3 values which are accepted previously. Okay, so after the proposer receive this, after this leader receive majority of the promises message, it can send an accept message. Okay, in the accept message, it will send current instance number, the proposal ID and the value which the leader want to propose. So here the value V is the value associated with the maximum proposal ID which we will receive in the promise message. Okay, here we will also there might a different possibility also here. If this proposer will not receive majority of the promise message, it will not do anything. Okay, it will initiate a next proposal with an incremented proposal ID. The second phase of accept and accepted message will not occur. Okay, after this after the proposer will send a accept message, acceptor will receive this accept message. If the acceptor didn't promise to reject the proposal with the proposal ID N, it will accept this message and it will send this accepted message to the proposer and all the learner. Now learner will learn this agreed value and learner will send it to the client. Okay, so the next case is multi-Paxos when phase 1 is skipped. As we discussed already, if the leader is stable, means the same leader is executing the next phase also, we can skip phase 1, means the leader will directly send an accept message. So here this leader is sending an accept message to all the acceptor along with the proposal ID n and the incremented instance number I plus 1 and value w which it want to propose. Now this acceptor will receive this accepted message, and as the acceptor didn't promise to reject any proposal with the proposal ID n, it will accept this value w, and it will send this accepted message to the proposer and to the learners. Now learner will learn this value and send it to the client. Okay, so the next case is multi-Paxos when the roles are collapsed. Means we will not have this proposer, acceptor, learner. All these roles are collapsed into a single role called servers. Means here we have only client and server simply. Okay, so now client will send a request to the leader. Now leader will send a prepare message with the proposal ID n. Now this server will receive this prepare message, and as the server didn't promise to reject any proposal with the proposal ID n, it will send a promise message to the leader along with the current instance number and previously accepted value if there are any. Okay, now this after this leader receive the majority of the promise message, it will send an accept message to the servers. Now this servers will receive this accept message, and if the server didn't promise to reject any proposal with the proposal ID n, it will accept this value vn, and it will broadcast an accepted message to all the servers. Finally a value will be agreed, and that agreed value will be sent to the client. Now our next case is multi-Paxos when roles are collapsed and the leader is study. Means the same leader is executing the next instance also. Now there are only client and server only. Now the client is sending an request to the leader on the behalf of client. This leader will send an accept message to all the servers. Now acceptor will receive this accept message, and if the server receive the accept message, and if the server didn't promise to reject the proposal with the proposal ID n, it will broadcast this accepted message to all these servers, and finally a value will be agreed, and that agreed value will be sent to the client.
What is fast Paxos? Fast Paxos is just a faster way to implement Paxos. Fast Paxos just generalizes the end-to-end message delays to reduce it down to a 3 message delay point. And what are those 3 message delay? It is the point from which the client request to the point when the learning phase is completed. Now this 3 message delay phase has been dropped down to 2 message delays in the fast Paxos. So how is it designed? In the fast Paxos, a round is either a fast round or a classic round. In the fast round, the client directly proposes the values and the learners directly send the result to the client. And in the classic round, the execution happens just the same as the classic Paxos. Now let's compare Paxos with the fast Paxos. Now this is a way how Paxos algorithm goes on, in which the proposer requests to the leader on the behalf of the proposer accepts a value, and the acceptor then sends an accepted value to the learner, through which the learner learns the value. But in the fast Paxos, the proposer skips the point of requesting it to the leader to send its proposal and directly request the acceptor, and then the acceptor send the accepted value to the learner to learn it. Now how does the fast Paxos even work? See, it happens in a single RTT completion phase. So in this RTT completion, there are 2 RTT phases. So both the fast round and the classic round take 2 RTTs in the beginning. In the first RTT phase, the message has been prepared, request and respond. In the second RTT phase, the accept request and response has been sent. Now the phase 1 can be omitted in the fast Paxos, but only when the initial state which is currently there should be just as similar to the previous state, or the messages in the previous round might indicate something that has not been changed in the current round. Now let's have a few look at the non-conflicting proposals of the message flow where fast Paxos is executed perfectly. Now look at the point where the leader and this acceptor point is shown. Here any previous transaction has been done and the only leader is there, so this is the perfect condition for a fast Paxos to occur. Now as the leader remains the same for the next transaction, so the client skips the leader and directly sends the accept messages to the acceptor, and then the acceptor pass on the accepted message to the learner, and the learner in response send the response to the client. Now let's have a look where there are some conflicting proposals in the fast Paxos. Now the situation is same over there, the leader is consistent and the client learns from the previous messages and they skip the part of the leader, and due to multiple clients, these both clients send message as the same point to the acceptors. Now the acceptors get confused and two acceptors decide to accept the value from the first client and two from the second client, and they forward the accepted message to the learners. Now the learners disagree because the values are different, and after this the phase is cancelled and the classic round begins where the leader propose the accept messages to the acceptor, and now they find out the accept messages from the leader and they forward it to the learners. Now the learners finding out that the value is same, so they send a response to the client from where it came. Now this part is the part where the collision is detected and then recovered. So now let's come to the topic of Byzantine Paxos. So before arriving to this topic, let's just forget everything we assume in the Paxos, because that doesn't have the features that have been included in the Byzantine Paxos. So the Paxos can also be extended to support arbitrary failures that include the failures of the participants, lying of the participant, fabrication of message by the participants, collusion with other participants, and much more. And now this type of failures are called Byzantine failures. The name was kept after one of the solution popularized by Lamport was been produced. The Byzantine Paxos was introduced by Castro and Liskop, which adds an extra message verify, which is used to distribute knowledge and verify the actions of the processors. That is, to check the integrity of the processor that had it really sent the message, or someone is acting as the processor to send the message. Now let's have a perfect look at the message flow in a Byzantine multi-Paxos. In this, first the client requests the proposer, and then the proposer on behalf of the client sends an accept message to the acceptor, and before passing the message to the learners, the acceptor first verify the message by broadcasting it, and once the verify message is completed, then the acceptor sends the accepted value to the learner, and then in turn the learner response is received by the client. So now what is fast Byzantine Paxos? So fast Byzantine Paxos is just an improved version in which the extra delay part is been removed, which was introduced by Martin at LVC, since the client sends command directly to the acceptors. So in this, the leader part is again ignored that happened in the fast Paxos. But the difference between this is that the fast Paxos sent accept messages only to the learners, but this send messages to the acceptors as well as the learners. Now let's have an example of the message flow in the fast Byzantine multi-Paxos. Now as you can see over here, the proposer part has been missing. The client directly sends a message to the acceptors, and the acceptors broadcast the accepted message to the learners, and then the response has been received by the client. And here you can have a look, the verify message has also been missing, that has been removed in the fast Byzantine multi-Paxos. Now let's have a look at the fast Byzantine multi-Paxos fails. Now again the client sends some messages to the acceptor, but let's have a close look. Here this acceptor is a faulty one, so this will not send the messages it received. So when the client sends the message accept message to the acceptors, it is then forwarded to the learners, but the learners receive different values. So as when the learner received two different commands, they noticed that and they didn't accept the value. Then the acceptor sent the accepted value again, and this time the faulty processor also sent the same message, but the majority is then received. So the learner accept this message and send the response to the client.